To continue the reactions and compounds of group 14 elements, we see the carbon tetrahalides. They are not obtained by the direct reaction of carbon with the elemental halogens but by direct indirect methods such as the reactions where X is chlorine or bromine, CH4 plus X2, that is halogen, reacts and gives carbon tetrahalide. These carbon tetrahalides have the tetrahedral geometry predicted by the valence shell electron pair repulsion theory, that is VSEPR model. For CCl4 and Cl4, their stability decreases rapidly as the halogen increases in size because of poor orbital overlap and increased crowding. Because the CF bond is about 25% stronger than a carbon-hydrogen bond, fluorocarbons are thermally and chemically more stable than the corresponding hydrocarbons, while having a similar hydrophobic character. A polymer of tetrafluoroethylene CF2 double bond CF2 analogs to polyethylene. It is the non-stick Teflon lining found on the many cooking pans, and similar compounds are used to make fabrics stain resistant or waterproof but breathable. The stability of carbon tetrahalides decreases with increasing size of the halogen due to the increasingly poor orbital overlap and crowding. This is the point to notice again. Now we see the carbon reacts with oxygen to form either carbon monoxide or carbon dioxide, depending on the stoichiometry. Carbon monoxide is colorless and reacts with iron in hemoglobin to form FeCO, that is carbon monoxide unit, which prevents hemoglobin from binding, transporting and releasing oxygen in the blood. So, in the laboratory, carbon monoxide can be prepared on a small scale by dehydrating formic acid with concentrated sulfuric acid. The reaction given here shows the formation of carbon monoxide. Now, carbon monoxide also reacts with halogens to form oxohalides. Probably the best known of these is phosgene, that is Cl2C O, which is highly poisonous and was used as chemical weapon during World War I. You might also have heard that this is prepared as CO, carbon monoxide reacts with chlorine to give Cl2CO. Despite its toxicity, phosgene is an important industrial chemical that is prepared on a very large scale, primarily in the manufacture of polyurethanes. Carbon dioxide can be prepared on a small scale by reacting almost any metal carbonate or bicarbonate salt with a strong acid. As is typical of a non-metal oxide, carbon monoxide reacts with water to form acidic solutions H2CO3, carbonic acid. In contrast to its reaction with oxygen, reacting carbon with sulfur at high temperatures produces only carbon disulfides, CS2. The selenium analog, CSE2, is also known. Both have the linear structure that is also predicted from VSEPR, that is valence shell electron pair repulsion model, and both are while smelling, and in the case of CSE2, that is highly toxic volatile liquids. The sulfur and selenium analogues of carbon monoxide, CS, carbon monosulfide, and CSE, are unstable because C triple bond Y, where Y represents sulfur or selenium, are much weaker than the carbon monoxide bond due to poorer pi orbital overlap. Pi bonds between carbon and the higher chalcogenides are weak due to the poor orbital overlap. Binary compounds of carbon with less electronegative elements are called carbides. The chemical and physical properties of carbides depend strongly on the identity of the second element, resulting in the three general classes. And The reaction of the carbon at very high temperatures with electropositive metals such as those of group 1 and 2 and aluminium produces ionic carbides which contain discrete metal cation and carbon anions. The identity of the anion depends on the size of the second element. For example, smaller elements such as beryllium and aluminium give methides such as Be2C and Al4C3, which formally contain C4- ion derived from methane by losing all four hydrogen atoms as protons. In contrast, larger metals such as sodium and calcium gives carbides with stoichiometries of Na2C2 and CaC2. Because these carbides contain C4- ion which is derived from acetylene by losing both hydrogen atoms with protons. They are more properly called acetylides. As discussed, reacting ionic carbides with dilute aqueous acid results in the protonation of the anions to give the parent hydrocarbons, that is methane or C2H2. For many years, miners' lamps used the reaction of calcium carbide with water to produce a steady supply of acetylene, and this acetylene was ignited to provide a portable lantern. The reaction of carbon with most transition metals at high temperatures produces interstitial carbides. Due to the less electropositive nature of transition metals, these carbides contain covalent metal-carbon interactions, which results in different properties. Most interstitial carbides are good conductors of electricity. They have very high melting points. They are the hardest substances known. Interstitial carbides exhibit a variety of nominal compositions and they are often in non-stoichiometric compounds whose carbon content can vary over a wide range. Among the most important are tungsten carbide, that is WC, which is used industrially in high-speed cutting tools, and cementite, which is a major component of steel. Elements with electronegativity similar to that of carbon form covalent carbides such as silicon carbides SiC and boron carbide B4C. These substances are extremely hard, have high melting points and are chemically inert. For example, silicon carbide is highly resistant to chemical attack at temperatures as high as 1600 degrees centigrade because it also maintains its strength at high temperatures. Silicon carbide is used in heating elements for electric furnaces and in variable temperature resistors. Carbides formed from group 1 and 2 elements are ionic transition metals from interstitial carbides with covalent metal-carbon interaction, and covalent carbides are inert. Now, other than carbon, we'll see the reactions and compounds of the heavier group 14 elements in the next lecture.